All right, part 4 of the single trial series is going to focus on variable extraction or calculation. So specifically everything we've done up until now is to import the trial, process that trial with some filtering if we do or do not decide to do that. We discussed some integration needs, phase identification, and touched on how filtering may or may not impact that phase identification, kind of briefly in there. Now is kind of the fun part, and it is how we extract or calculate variables from what we've got. So I've left off where we were at the end of part 3, and we've ended up with the landing and jumping phase definitions here. Okay. So what I'm going to do here is I'm just going to go ahead and clear out this command window because it's a little dirty in there and I don't like that. And let's add some space to the bottom of our script so we can work with it and give us a little more room. All right, so now variable extraction and calculation. So I like to start this kind of sequentially for variables in order of importance. So that means we'll start off with performance variables. These are analogous to what some call output variables, but they're the main metrics at which we use to compare performance gains, and they're the main variables we're trying to manipulate one way or another. It's really irrelevant what changes beneath these in terms of how to manifest changes in the output variables. So these are the performance variables, and these are important. So we'll start, because this is a counter movement jump, with the granddaddy of all performance variables for the jump historically, which is jump height. Now we can calculate jump height a number of ways. We can do so using the impulse-momentum relationship, which requires us to do some integrations and some other secondary calculations after we get there, which is all fine and good. I tend to want to calculate flight height, so only the height traveled moving upward. So I won't use other methods like time in air or anything like that. We'll just use an equation of uniformly accelerated motion and go from there. So the equation we'll use for jump height is to take takeoff velocity at the time of takeoff. It's kind of a redundant thing there, but velocity at the time of takeoff, we'll square it and divide it by 2 times the acceleration due to gravity. So what we'll do here is we will create that jump height, and we're going to take our velocity at takeoff. We're going to square it, so we use a caret with the squared, and we will divide by 2 times the acceleration due to gravity, which is 19.62. Now we'll use the absolute value for that acceleration due to gravity to calculate that variable. Okay, and so calculate that. We'll look over here, and we'll see that jump height for this athlete was not very high, 17. We'll give it the benefit of the doubt and round that up to 18 centimeters. Okay, so let's just note here that that was units of meters. Okay, and there we go. The next variable that we might want to look at is jump momentum. There was a good video recently put out on the importance of jump momentum as it relates specifically to collision sport athletes. So those of you who may work with those type of athletes should be interested in that takeoff momentum. Now we can also, for this method, do some integrations, calculate impulse, and then know from the impulse-momentum relationship that those two things are equivalent parameters. But there's a much simpler way, and if we think of momentum being mass times velocity and we want takeoff momentum, Well, we'll take takeoff velocity and multiply it by mass. Okay, so what I'll do here is I'll go momentum. This will equal the velocity at takeoff, and we'll just multiply by our mass. Now this is meters per second in kilograms, so if I want to do this the formal way, I'll do mass times velocity at takeoff, and this will return units of kilogram meters per second. Okay, so if I pump that in here, we'll see that momentum right there was about 257 kilogram meters per second. Okay. The next variable that I consider to be a performance metric is the modified reactive strength index, which is the jump height divided by the jump time. Jump time also sometimes referred to as time to takeoff. So in order to get that, we'll use our RSI mod. Now we already have a calculation here for jump height, so let's go ahead and copy that. Okay, so that's our jump height. Now we'll put that into parentheses to make sure our order of operations holds. And we'll divide this by the time from start of the movement to takeoff. So what we'll do here is time, and open a parenthesis and say at takeoff minus time 1. Now the reason we're doing that, and we put these obviously in our parenthesis so that the order of operations hold, and it's actually jump height divided by jump time. Okay. Now since if we look at time number 1, well that's actually the start of the counter movement. So you could actually just do time of takeoff, because if I did time takeoff, you'll see that's 0.77 seconds. And then if I did what I've done here, time takeoff minus time 1, it's 0.77, right? So it's the same, but that's dependent on whether or not we trim the trial so that the first data point of what we're working with in the processing is at the start of the counter movement. If it's not, you'll need to specify here at the start of the jump. But if you followed the process that we've done throughout these videos, this will work just as well as this. Okay? And so this, I like to call these arbitrary units. Now technically, if you take this, it's a meter for jump height divided by a second for time. Since those two things, the time frame at which we get the time is not the same time interval related to kind of the jump height counted at the end, so it's not really your velocity, right? So saying that's meters per second, I think would be kind of inappropriate there. So I call those arbitrary units, and we can just say that, you know, because it's an index variable, it means the same kind of thing, arbitrary units. But when we calculate that, we'll see that RSI mod, the modified reactive strength index of 0.23 arbitrary units. Now this may be where you're done with those performance variables. You may have an interest in jump, peak power. I think if you're using a jump height measure, peak power is kind of irrelevant and a redundant measure because the prediction of peak power and jump height is almost perfect. So we wouldn't need to do that. Here you wouldn't need to do an impulse, or at least a propulsive impulse, because that impulse is the determinant of jump height. So if you have jump height, you essentially understand the impulse. More jump height would mean more impulse for a given athlete, assuming body mass and things of that nature are the same. So you wouldn't necessarily need that. Also, because you've got the momentum at takeoff, you wouldn't need that variable either. So we won't do any integrations here for impulse. Okay, what we will do now is move on to what I like to call strategy variables. Now, those strategy variables can account for both time, temporal, and force application. Some divide those strategy variables into, I kind of have one umbrella strategy, but some use strategy for temporal and, gosh, what do they call it? Driver for force variables and rate of force development variables. I just kind of put those all under strategy because I think those all kind of relate to each other, but I'll just kind of personal preference there. So what I'll do is go strategy variables, and I'll start temporally. Let's start with the time of the jump. And so what we'll do is jump time. Now you can also call this time to take off or TTT, whatever you want to call it. But this will simply be time at takeoff because we know that that is, we've already discussed that here for RSI mod, how to get that. But it would also be the difference in time from takeoff to the start. So if we wanted to do it formally, it would be written as time at takeoff minus time at the first data point, final minus initial. Those are going to get me the same values for the reasons we talked about previously, so I'm just going to simplify this here. All right, 0.77 second. All right, now what we'll do is start with the individual phases. I'll start with the unloading time. So the unload time would be time at unload end. Now I could subtract out time at the first data point. Again, reasons we've talked about, I don't need to discuss that. Again, don't want to beat a dead horse, so we're just going to use time at the unload end. All right, 0.11 seconds, pretty fast unload for this trial. We'll then go sequentially through the phases I defined in the previous video. And so what we'll do is now the eccentric yielding time, and just to be more abbreviated with my variable names, I'm just going to call it yielding time. Now we're going to need to do a final minus initial math because the start time here is not going to be 0. So this will be time yielding end minus time unload end, and that will be units of seconds. This will hopefully be a little bit longer, just a little, 0.18 seconds. Now we'll pull out the braking time. Again, this is eccentric braking based on the phase definitions used, but shorting, typing while I talk, but we're going to short it to just braking for brevity, and this will be time braking end minus time at yielding end. Okay, and this will be units of seconds as well. This will be what, 0.28 maybe? Oh wait, do it one more time. Oh, that was fast braking time. All right, then the final phase, what we'll do here is we'll actually do an eccentric time. That's really just the sum of braking plus yielding, but you may be interested in looking at the eccentric phase as a whole and not breaking it into its subphases. So let's just go ahead and do that. And this would end up being time from the end of the braking, so braking end, minus time at the start of yielding, which would be unload end. Okay, and then this will be 0.38, right? It's the sum of yielding and braking. The final time we'll use is concentric time. This is just the time between the end of braking and takeoff, so it'll be time at takeoff minus time at the braking end. And again, units of seconds. And there you go, 0.28 seconds for concentric time. Now those are the temporal strategy variables. Those ones are easy enough. When we get to the force variables, it gets a little more difficult. Now, there's some papers that have been published previously about importance of certain variables that we can extract using this phase deconstruction method. One is this paper here from Leland Barker at Creighton University, where he's using relationships among different variables and jump height and RSI mod. So you can see it's using our unload definition we have here, eccentric and concentric. and there's a number of variables that are talking here. Now, one of those variables, without spending too much time reviewing that paper, is the unload amount, so how much the user unloads. And we're going to use that variable to kind of hopefully use a better interpretation, at least an easier interpretation from a coaching perspective. So rather than saying, if I were to, let's just do, and just pull in the command window, let's just not script this, but we'll take the force value, FZ, at unload end, right? 615 newtons. Now, most cases we want to normalize these variables to some sort of parameter like mass or weight. If we divide that by weight, we'll get 0.45 body weights. If we divide this by mass, we'll get 4.45 newtons per kilogram. Now that's all fine and dandy. That tells us what the force value itself was at the end of unloading, but it doesn't really give us a functional metric. So what I'm going to end up using here is the percentage of body weight that was unloaded, so that a larger number is going to mean you unloaded more of body weight. Here it would have to be, if we do it here normalized to just the weight by itself alone, a smaller number would mean you unloaded more, right? So that can get a little confusing. And so we're going to use it as a larger number means more unloading. So let's do unload FZ. Now what we're going to do is convert this to a percentage and normalize to body weight, so the percentage of body weight that gets unloaded. So to do this, we're going to open a parenthesis and use 1, because that's going to be our standard to create the difference in one body weight versus where they are to create the percent. So we're going to do 1, we're going to subtract from that in another parenthesis the force value at the end of the unloading phase. We're then going to divide that by weight and close that parenthesis. So inside this second parenthesis here, this here is the normalized force, which we calculated up here to be 0.45. Then we're going to do 1 minus that. Okay. And then what we'll do is multiply by 100 to convert that to a percentage. So this becomes a percent of body weight larger equals more unloading. Okay, and I'll just add my semicolon to suppress that. Copy this to the command window and just to calculate. You'll see there about 55% of body weight was unloaded. Okay. Now, next unload variable that could be useful is the rate of force development during the unloading phase. So if I plot the FZ just for the jump, so just to take off, and I add a vertical line at the end of unload, we're talking here, so we pulled out this value as the unload FZ and converted it to a percentage of body weight. Now what we're talking about is this rate of force development. Now this brings up an issue I have with the term rate of force development, because we're not developing force, we're reducing force. So really a rate of force reduction, but that doesn't sound very useful or commonly used. So we're going to talk about this being a yank value, because negative yank is useful. But if you just think of this as rate of force development, that's the way you want to run with it, we can do that. Just understand that is going to be a negative rate, and that is useful. So you aren't developing force, you're reducing force. And we're going to take the average rate of force development in this time period. Now, just to show you what you would do if we wanted to take the, find a peak rate of force development in that time, what you would have to do is, so if I did this as unload RFD, you would have to use the cumulative, well, actually no, you wouldn't. You'd have to use a diff. It's not an integral, it's a differentiation. To do differentiation, you would use MATLAB's diff function. So it would be diff fz from 1 until the unload end, divided by, now since we're using, if you notice here, time, we're going to divide by time, but since time is not one value, and we want to do this at each element or each data point, we have to use a dot product. So it would be dot divided by difference in time from 1 to takeoff. Okay, so that would be how you do the cumulative derivative. Now the problem with this is this MATLAB, it's an approximate derivative, and so you think you're taking the difference between two time points, so you're actually getting the time point kind of at 1.5 instead of at data point 1. So you're going to end up with one data point that's too short. So what you can do here is, at the start of this, is add a bracket, put a 0, and then a semicolon, which will kind of tell that to become a set of rows. So the 0 will be the first row, and then whatever's after it, the diff equations, will become the next bit of rows. Okay? And then at the end of this, we'll close a bracket here. Now what that's going to do is keep it at length of 4903. Use type takeoff wrong. Gotta make sure you spell it right. Ooh, and I'm getting the dimensions disagree likely because I tried to do this without specifying that there are two unique, what is one unique array right here. That's a unique deal. So what you could do instead is actually get rid of that and do this. Oops, of course I typed it wrong. Now why? Oh, this is why. I'm a goof. Notice I used the time here of the unload, and then I did time of takeoff. That's why my dimensions don't agree, because they're different lengths. Of course, we want the unload RFD. So that probably means my previous attempt would work. Unload RFD. Oh my gosh. Look at all these boo-boos. Let's do what we need to do here. Unload end. Gosh, I can't even remember what the own variable names were. There we go. So there's that derivative. It pops into the command window. Took long enough, right? But you'll see here, 108 frames. That's the length of the unload phase. And then from this, what we would need to do is, let's see if this will work by putting in what we had originally. All right, you'll notice right here, this unload was 108. It technically should be 109. There it is. Okay, so what I've done is replace this first data point with a 0 to align it appropriately. Okay, and if we're wondering, well, what in the heck are you doing that for? Because if I did how many data points were at time from 1 to unload end, 109. And so we want the times to match up correctly. We don't, or the number of elements to match up correctly. Okay, and then after this, if you wanted to get the maximum or the peak rate of force development, we have to recognize that this is a negative, right? The force is changing negatively, so we'd want the minimum. And so that would be unload RFD min, whatever you want to call it, and take the minimum value of unload RFD. Okay, now this is non-normalized. Okay, now if I wanted to, I would take this and normalize it to weight, and that would be body weights per second. Okay, now just to put a note here, this was cumulative derivative. Well, I guess we don't need to say cumulative, we can just call it derivative. But it's the element-wise, it's not a single value. This here would be peak the minimum, to be specific, RFD during unload. Some people enjoy those peak RFD values, in this case a minimum, so you could do that again for the other subphases. I'm not sure how much that tells us in terms of functionality, because that's one rate of force development at one data point, so at 1,000 frames of data collected, the peak rate of force development or the rate of force development over 1 millisecond is how much information do you get from there. So I'll just go ahead and take these and comment those out. We'll leave them there because they work, but we're going to end up using the average rate of force development. So I'll create a new unload RFD, and this is simply going to take the difference in the force values from during the unload phase and divide it by the difference in time during the unload phase. So it's going to be a much more simplified variable that still shows some strong relationships to overall jump performance. So what we're going to do here is open a parenthesis, and we're going to go FZ, and we're going to go unload end. We're going to subtract FZ at 1, because that's the start of the jump. We'll close those parentheses, and we will divide by, we could technically divide by unload time, but let's just keep this as a calculation. That way there's no confusion in terms of whether or not it's trying to recalculate this time or pull from this variable, just to keep things straight. So there's that. If I want to, I'll end up dividing this by weight, so the units will be in units of body weight per second. Then we'll see the average rate of force development during the unload phase was negative 4.8 body weights per second. So we'll add the units there. Okay, so I find that to be a much more useful rate of force development to use in this phase. We'll move to the yielding phase. We will not. So if I pull back up the graph here and add the line for the end of the yielding phase, we don't want to pull the force value at the end of yielding right here, because if you understand what's going on mechanically, you'll know that that's equal to 1 body weight. And so if I put a line right here from that first data point all the way across, it's going to be right there, and it's going to be almost identical to that body weight value. So we don't need to pull that value. It would just be a redundancy and not tell us really much of anything. So we're going to skip right to the average rate of force development in this eccentric yielding phase. Now you could go through the processes we outlined for the unload phase to get the point-to-point rate of force development and then pull out a peak if you wanted to, but we're going to stick to the average rate of force development. So to do that, we'll do it just like we did with the yielding, or excuse me, with the unloading. And what we'll do is take the force value at the end of yielding. We'll subtract out the force value at the end of unloading. And we will divide by the difference in time from the end of yielding minus time at the end of unloading. Right, so it's just the difference in force divided by the difference in time. And at the end of this, we'll divide by weight to give this body weights per second. All right, and take away that. There we go, 3.03 body weights per second of average rate of force development during yielding. Now, what I think are the critically important variables, if we've kept up with the literature and recent publications that have come out, is that what's happening during eccentric braking is really the meat of the sandwich here, the counter movement jump, where the neuromuscular function changes really start to show. And there's two variables we'll use. We'll use the force value at zero velocity. This has been also referred to as the amortization force value, because at the time of amortization, or the transition from moving downward to upward, that's amortization. And so what is that force value? At that time, zero velocity is happening, so those are the same thing. Since we've got this defined as that being the end of the eccentric braking phase, we'll just call this the braking force or the braking FZ. Okay, but any one of those, it's all synonymous. This is the same thing as an amortization FZ or amortization force or a force at zero velocity. So we're talking about the same variable. So what we'll do here is we'll go braking, get rid of this, FZ, and we'll say this will be equal to the FZ at braking end, and we'll divide by weight so that this will be in body weights. Hopefully this will be something more than 2 body weights. Not quite, you can tell we don't have a very good jumper here. But 1.81 units of body weight of force achieved at that time period. Now this is kind of an important variable because some argue that it represents or is a reflection of the mechanical energy stored in the system, because if you think of Newton's laws, when you're not moving, right, there shouldn't be, you're standing still, there shouldn't be much force there. So whatever that is, that value being increased, that would be a useful variable there. There's some papers from Bobbert and I think from Comey back in the day covering that variable. So that's one that's kind of important. The second one we'll do will be the rate of force development during the braking phase. That's the average rate of force development, and hopefully now we're thinking, okay, I understand how to get the average rate of force development from doing it for unload and braking. But let's just go through it. And again, this is going to be the difference in force divided by the difference in time for that phase. So we'll take the force at braking end, we'll subtract the force at yielding end, and we will divide by time braking end minus time at yielding end. So we'll do that. We will divide by body weight, so we get body weights per second. And this would be the rate of force development when braking. Oops, I typed in braking end wrong. All right, I didn't use a capital right here, which I need to. So MATLAB will fix that for me here. But I'll fix it here in the code. So just over 4 body weights per second when braking. Still not a good value, but one we want to monitor. Now, just to avoid redundancy and doing the same variable over and over again, I won't do this for the overall eccentric phase, but just recognize that what we would do is take force at braking end minus force at unload end divided by time at braking end minus force at unload end. That would be, in this case, based on these phase definitions, the average rate of force development over the overall eccentric phase. Another variable, I'm not a super huge fan of concentric variables, but you may want to look at the average force during the concentric phase. Some show that being a kind of useful metric to look at. So we'll go ahead and add that one in. So we'll call this concentric FZ. This is simply going to be the average, or in MATLAB's case, we'll use the mean. We'll take the mean of the force, or the FZ, between braking end and takeoff. Right, so that's the average force during the concentric phase. We close out our parentheses to fit the order of operations, and we'll divide by body weight so that this will be in units of body weights. And we see an average of 1.67 body weights of force during that concentric phase. Other concentric variables you may look at, like I've said before, might be peak power or other strategy variables that could be useful. So let's do some kinematic strategy variables. We'll do 2. We'll do counter movement depth. So we'll do depth. This is the only variable where we'll use the position. You don't need to use the position, but it's the most direct calculation. So you could use the velocity and the time values, do some multiplication. and get those there, but what we'll simply do is say the position, because we calculated it, at braking end subtracted by the position at the start, which is 1, right? So that will give us that value. It will be in meters. And again, this is a vector quantity, final minus initial, so we're going to end up with a negative value for that depth. And it's in units of meters, so that's 0.24 meters, or 24 centimeters downward. Another variable that I've started to see value in after reading a paper from Pierre Samazino is push-off distance. Because we look at depth as a critical variable, but we usually don't look at, the upward displacement that's happening, because you could have two athletes or an athlete go through the same depth from trial to trial, but they end up going through a different push-off distance. Maybe they've extended more triple extension at the end before takeoff, what have you, and they can actually perform more work, and that could be a revealing mechanism for a change in jump performance. So we'll add that push-off distance here, and I'll just call it push-off dist just to be simplified. But what this will be is the position difference from takeoff between and takeoff at the end of eccentric braking. So the concentric phase, it's what's that displacement they travel. Okay, and this will be in units of meters. Now this, if we compare depth, that was 24 centimeters was depth. Push-off distance will obviously be a positive value based on how it works as a vector. But you can see it's 34 centimeters, so there's actually 10 centimeters there of extension beyond that at which they were at when they started the counter movement. So they, do some manipulation there that could reveal some changes in your interpretation if you don't have that value. Can you say, well, none of the force values or rate of force developments or strategies in terms of time changed, but jump height and RSI mod, all those things changed? It could be because they went through more distance when they pushed into the ground during the concentric phase. And so just something to reveal there. That could be especially useful if you're working with basketball athletes and you got guys of wildly different heights. You may want to create some sort of control for that push-off distance when you think of height achieved. All right, very quickly to go over landing, because the landing variables are going to be quite similar here. We'll just do landing, and we'll just run through a couple of them. The height, landing height and impact momentum, you're going to calculate exactly the same way we've done here, except for instead of using takeoff velocity here, we'll use velocity at ground contact. Okay, so that's going to be the only change that happens here. So I'm just going to copy these two lines, change jump to landing, and then we'll add landing here to momentum. And then what we'll do is change this from being takeoff, it'll be ground contact, ground contact. Now in a perfect world, these two values would be identical to the jumping heights. But if we look, jump height was 0.175, landing height was 0.144. So we've done a little bit of manipulation of the body position here in terms of the distances traveled. That's obviously going to change the momentum as well. Okay, other variables that would be important here. We'll talk about strategy variables. I would think of let's do one for performance, because landing performance is really quantified by how fast you can complete the landing. So we'll do landing time. This will be the time from the end of the landing, which we called as the phase land end, and it will be minus the time at ground contact. Right, and that'll be in units of seconds. And if we run through this variable, 0.39 seconds to complete the landing. So to terminate that downward momentum, which they have 232.5 kilogram meters per second, it took 0.39 seconds. Right, so some landing performance characteristics. Now what we'll talk about are the landing strategy variables. This will be time and depth. The time variables are going to be calculated just like we did above, but using the appropriate endpoints and starting points to do the final minus initial time. So I won't type those in here. When we get to the next video, I'll just have them there to save us that time. But what we'll talk about are the peak force, the average force, and perhaps the loading rate. So we'll real quickly cover those. So the peak force, if I close this and I just plot FZ from ground contact to land end. So we're only looking, oops, gotta make sure I use the right symbols here. Right, we're looking at the peak force. We'll look at the average force to get to this time point, and we'll look at the average rate of force development here. All of those can be thought of as injury risk variables. If we think about external force and its relationship with stress fractures, it's about as far as we want to take injury risk from those impact forces. You might make some inferences based on the data as to whether or not a loading rate might relate to joint-specific injuries, but I think it's too indirect of a claim to make at this time. So we'll just stick to stress fracture kind of risk as it relates to those impact force variables. So what we'll do, let's take impact peak FZ. This is going to be the FC at loading end, because remember we defined a phase by that time point. We'll divide by body weight. And this will be in units of body weights. This will be a pretty large one if you inspected the curve and known how high that was. So you see 5.5 or 5.6 body weights of impact during that vertical jump. The average, we'll take impact average FZ, and we'll use the mean equation, and we'll take the average of FZ between ground contact and the end of landing. And then what we'll do is divide that by body weight to get this to be in body weights. So 1.45 was the average. Oops, I didn't want land end. That's my fault. We want loading end. That obviously would change that value quite drastically. So there we are. Now, get some space. And let's do the rate of force development. So, this is usually called a loading rate, right? Because it's an impact and a loading characteristic rather than a force development. So we'll call it loading rate. And this will be the change in the force, which is the FZ at load end minus the FZ at ground contact. We'll divide by time at loading end minus time at ground contact. Okay. Then we will divide by weight. Turn this bad boy into body weights per second. Okay, you can see that's a pretty sufficient or substantial rate of force development or loading rate on that athlete. It's a lot of body weight per second. On the back end, we may be interested in attenuation. So if you thought about up here, our variables we did for attenuation, and so now we can do between loading and attenuation based on those kind of hypothetical new definitions we're talking about. But what we can do here is take the average force during attenuation. Obviously, less force would mean more attenuation depending on the peak FZ, right? If peak FZ doesn't change, but attenuation FZ decreases, we've done a little more attenuation. So it might be something you care about. So let's just do that. That's going to be the mean of the FZ between loading and attenuation. And we'll divide that by weight to get that in units of body weight. All right, so the average attenuation was 1.67. Now to get the rate of attenuation, how quickly and rapidly that force can be attenuated, let's do an attenuation rate. This is a variable that we've found to be, well, with a slightly different definition, to be related to landing performance. So if you can have a faster rate of attenuation or a higher rate of attenuation, you're probably going to land faster. So we'll look at that. You know, it's only one paper to see that kind of variable, so it may not be critically important, but let's just pull it out here. This will be the force value at attenuation end. We'll minus the force value at loading end, and we'll divide by time at attenuation end minus time at loading end, and divide by weight. This will be in body weights per second. Now again, because the force is decreasing during attenuation, that's going to be a negative value. So you can see they attenuated at almost 30.3 body weights per second. So there's those variables. When we come back, we'll talk about how to export the data, just simply so that you can visualize the data or create some graphs that you may be familiar with, whether that be in Excel or SPSS. So the next bit is going to be just a simple way to organize the output variables.